In this video, we're going to look at separable first-order differential equations. And we are talking about ordinary differential equations, so we're not talking about partials, derivatives, or partial differential equations, I should say. So the first thing I want you to do is, as a warm-up, is to factor, right? So if we take a look at our first example here, there's a reason we want to start out with factoring. This is a nice refresher for factoring. Now for this first example, we have 4 terms, and so we think maybe we can factor by grouping. So if we factor by grouping, we can factor out a t squared out of the first 2 terms, leaving me x plus 1. And I can factor out a negative t out of the second 2 terms, leaving me x plus 1. And then you can see that x plus 1 is common, so I can factor out that x plus 1, leaving me t squared minus t. And this factors more. I can factor out a t out of that second grouping, so I have t, x plus 1, and then t minus 1. And here it is factored. Nice, easy factoring refresher. For the second example, we can factor out an x, leaving us t plus 2. And then for the third example is you cannot factor, does not factor. Now you're thinking, why did we start out with this? Well, we are going to define what it means to be a separable differential equation. So it's a first order. So in other words, I'm looking at my first derivative, so x prime, which is a function of x and t, is a separable equation if the function f can be expressed as the product of a function of t and a function of x. That is, we can take this differential equation and write it as p of t multiplied by h of x. So as an example here, if I have x prime, which is equal to p of t h of x, then I can divide both sides by h of x, and I got 1 over h of x multiplied by x prime is equal to p of t. Then q of x times x prime is equal to p of t, where I can replace 1 over h as q of t. If this can happen, then x prime is equal to dx dt, and q of x dx dt is equal to p of t. That means I can separate it. So it's q of x dx is equal to p of t dt, which means that we can integrate both sides, right? So I can integrate the left side, which is a function of x of t, x prime of dt, and then the left side, the right side, excuse me, of p of t dt plus c. Now, since we know that x is not x, it's a function of t, x is a function of t, and x prime is dx dt, then x prime dt is equal to dx, because of the fact that if I take dx dt, and that's what x prime is equal to, and x of t, then we end up with just dx. So then q as a function of x of t of x prime is just q of x dx, and we get this. This is the gist of it. So we have q of x dx is equal to p of t dt plus some constant. Then capital Q, which is the antiderivative of x, is equal to the capital P, which is the antiderivative with a function of t, plus c. And these are going to be the integral curves, the antiderivatives, the p of q, the q of x, the p of t with capital plus c. These are called the integral curves of the equation of q of x, x prime is equal to p of t. The implicit solutions defines the relation between the unknown x and its dependent t. And the explicit are the ones in which can be solved explicitly of x as a function of t. So the first thing you want to do is determine whether or not you can separate them. And then if you can separate them, you're going to write them as g of x of t, x prime, p of t, and then you're going to integrate both sides. So first of all, can you separate them? And if you can, then you are going to separate them. And then once you separate them, then you're going to integrate both sides, q of x dt and p of t dt. And then after you've separated and integrated it, you're going to write it as a solution of q of x is equal to p of t plus c. And these are capital, so these are the antiderivatives. And then solve the equation from the previous steps explicitly as a function of x, as a function for x as a function of t. And that was a mouthful. So an autonomous first order differential equation is a special case in which g of t is equal to 1. This doesn't happen very often, but it's nice when it does. And x prime is equal to h of x. And it cannot be solved with simple integration. So if h of x is equal to 1, then the integration of x is equal to the g of x dt. So let's go ahead and do some solving here. So the first thing I ask myself, is this separable? Can I get all of my x's to one side and all of my t's to the other? That's the first question I ask myself. Are they separable? And if they are, can I solve them by doing it as a separable differential equation? So the first thing, I'm going to say, hey, you know what? Let me multiply both sides by x, because I really want t by itself. And when I do that, I'm going to get x prime is equal to negative t. That means I can go ahead and integrate this. So I have the integration of x dx is equal to negative t dt plus c. So I'm going to go ahead and integrate this and regular rules of integration. So as you know, I like to do in green. I'm going to add 1, divide by that 2, add 1, divide by that 2. And so I end up with x squared divided by 2 is equal to negative t squared divided by 2 plus c. Now, if I multiplied everything by 2, I would end up with x squared is equal to negative t squared plus 2c. But 2 times any constant is still a constant, so x squared is equal to negative t squared plus c. Now, if I bring the t to the other side, I'm going to get x squared plus t squared is equal to c. And now this is an equation of a circle. This is an equation of a circle centered at the origin whose radius is the square root of c. This is an example in which I cannot solve this explicitly. And what I mean is I'm not going to get x is equal to. Because if I try to do x is equal to, whether I did it here or I did it up here before I went ahead and brought the t squared to the other side, I'd end up with a plus and minus. So I end up with 2 equations. So I can't actually solve this one explicitly. So my answer then is just this. Let's go ahead and take a look at my next example. So my next example, I really want to get t by itself. So the first thing I'm going to do is say, hey, can I get t by itself? So I'm going to factor. And this is why I started out with a factoring. And so I have x prime is equal to, I'm going to factor an x out of the numerator, leaving me t minus 1. In the denominator, I have x plus 1. So I'm going to multiply both sides by x plus 1 over x. And the reason I'm going to do that, x plus 1 over x, is that will get me just t minus 1 by itself. So I end up with x plus 1 over x multiplied by x prime, which is equal to t minus 1. Now, I know I can integrate both sides. I'm going to integrate this left side. When I integrate this left side, I'm going to write x plus 1 over x as x over x plus 1 over x. And so in other words, I have 1 plus 1 over x dx is equal to the integration of t minus 1 dt plus c. So I end up with x plus the natural log of the absolute value of x, which is equal to t squared divided by 2 minus t plus c. Now I can bring the t squared plus over 2 and the minus t to the other side. Absolutely do that. But what I do know is I cannot solve this explicitly because I can't factor an x out of this. The best I can do is try to write this as e raised to the, but that's not going to help me really very much because the problem that I have is I can't solve for x. I can't factor an x out, so I can't solve for it. So I cannot solve for this explicitly. So this is an implicit one. Taking a look at c here, I'm going to ask myself, can I get x all by itself? Or actually not x by itself, but can I get x's on one side and t's on the other? So what I'm going to do is I'm going to use a little bit of my algebra that says if I have e to the x minus t, this is the same thing as e to the x multiplied by e to the negative t. So then I can bring this e raised to the x to the other side, and then I have just one side of t and the other side of just x. So I'm going to divide both sides by e to the x. So I have e raised to the negative x prime is equal to t, e raised to the negative t. Now I have t's on one side and x's on the other, so I was able to separate this. I'm going to integrate both sides. So I have e to the negative x prime is equal to the integration of te to the negative t dt plus c. Now the left side is pretty easy to integrate. It's not bad to integrate, but the right side I do need to do integration by parts. When I integrate the left side, I'm going to get e raised, or negative, excuse me, I'm going to get negative e raised to the negative x. And on the right-hand side, after I integrate by parts, I'm going to get te raised to the negative t plus e raised to the negative t plus c. And for this one, I can take the natural log of both sides, which means I actually can solve this explicitly. So before I take the natural log of both sides, I'm going to multiply everything by a -1 so that I can make this a positive e raised to the negative x. So I have e raised to the negative x is equal to negative t e raised to the negative t minus e raised to the negative t minus c. But that's still just a plus c, by the way. Now I'm going to take the natural log of both sides. I'm going to take the natural log of this side. I'm going to take the natural log of this side. And when I take the natural log of the right-hand side, I'm going to get negative x is equal to, and then on the other side of the equal sign, I'm going to get the natural log of. Now, because these are all negatives, that means they all go in the denominator, so it's 1 over te raised to the negative t minus e raised to the negative t, that's a minus, plus c, because, all right, I could do minus c, but it's just a constant, so it doesn't really matter. Put on the absolute value there because I have to make sure that that's positive. And so I can solve for this one explicitly, and so I'm going to divide everything by a negative again. And so I'm going to have x of t, or just x, if you will, is equal to the natural log of the absolute value of 1 over te raised to the negative t minus e raised to the negative t plus c. And that's my answer, and that's one I can solve explicitly. So it's the first time I was able to solve this explicitly. Let's take a look at my next example here. Now, obviously, I can divide both sides by 1 plus x squared, so I can bring that to the other side. So I have x prime over 1 plus x squared is equal to 3t. Integrating both sides, I'm going to have 1 over 1 plus x squared dx is equal to the integration of 3t plus dt plus c. Now the the left-hand side is the tangent inverse. So 1 over 1 plus x squared is the tangent inverse when I integrate it. So I'm going to get the tangent inverse of x is equal to 3 over 2 t squared plus c. And this is another one that I can actually solve for explicitly. And you're thinking, how do I do that? Well, I'm going to take the tangent of both sides, and when I do that, I've got x is equal to the tangent of 3 over 2 t squared plus c, and that is my final answer. And if I want to, remember this is a function of t, so I can write this as x of t is equal to. Now what we're going to do is something similar to what we just did, except for now I'm going to be able to figure out what c is. I'm going to solve this initial value, and I'm going to be able to figure out what c is. So you can see that this is separable. So y prime is equal to, I'm going to factor out a y out on the numerator, leaving me x squared minus 1 over y plus 1. And then multiply both sides by the reciprocal. So I have y plus 1 divided by y prime is equal to x squared minus 1. Now I'm going to go ahead and integrate both sides. And when I integrate the left-hand side, and as before, we remember that I have y plus 1 divided by y is 1 plus 1 over y. So this is 1 plus 1 over y dy is equal to the integration of x squared minus 1 x squared minus 1 I don't know what happened there. So I have x squared minus 1 dx plus c. The left-hand side, I'm going to get y plus the natural log of the absolute value of y, which is equal to x cubed over 3 minus x plus c. Now I'm going to put in the fact that I know that when I put in x is 3, y is 1. That's what this reads. When x is 3, y is 1. So let's go ahead and solve for c. So I have 1 plus the natural log of 1 is equal to 3 cubed divided by 3 minus 3 plus c. Natural log of 1 is 0, so I have 1 is equal to 3 cubed is 27 divided by 3 is 9 minus 3 plus c. So I end up with 9 minus 3, which is 6. Subtract 6 from both sides, and I get negative 5 is equal to c. So my final answer is y plus the natural log of the absolute value of y is equal to x cubed over 3 minus x minus 5. And that's my final answer. And what this is a particular family member. Remember, we talked about this in my last video. This is a particular family member, whereas all the rest of them that I did prior to this example were a family of functions, where this is a particular family member. This is like the cousin or the sister or whatever. All right, and I'm going to let you do B on your own, and I'm go ahead and pause this, and then I'm just going to give you the answer. So go ahead and pause it right now. All right, so your answer when you get done is the natural log of the absolute value of x is equal to the negative natural log of t, absolute value of t, minus 1 over t minus 1. So that's your answer for B. Now we're going to go ahead and revisit population growth, and we've talked about population growth in other classes, and both in this class and in other classes. So we make the assumption that the population that we're looking at is P of t at some time t. We also make the assumption we have a constant birth rate of alpha and a death rate, not a date rate, death rate of beta per unit of time. Then the equation of the growth rate of the population, and it doesn't matter what we're talking about. It could be bacteria, it could be people, it could be mice in a field, is going to be equal to dp dt alpha p of t minus beta p of t, which ends up becoming, when I get done factoring out the p of t, is r p of t, where r is the net growth rate, which could be decreasing or it could be increasing. We know that this is a separable differential equation, and it has the general solution of p of t is equal to k e raised to the rt, where k is the initial population. And when we start studying our population, whether it's bacteria, mice in a field, or human population, k is the initial population when we start our study. Because a population cannot grow exponentially forever, there's going to be at some point the growth rate must decrease to the point that either it levels out and there's no more population increase, or it levels out and then it starts to decrease. So when that happens, we end up with P of t is equal to n over 1 minus CE raised to the RT, and this is the carrying capacity of n. And we've talked about this in the previous video as well. So let's go ahead and do an example. So scientists have observed that a small colony of penguins on a remote Antarctic island obeys the population growth law. There are 2,000 penguins initially and 3,000 penguins 4 years later. How many penguins will there be after 10 years? So the first thing we know is that this is P of 0, which is our initial population, is 2,000. We also know that we have this P of t is going to be equal to the 2,000 e raised to the RT. Now we also know that P of 4 in 4 years, we're going to have 3,000 penguins. So we're going to set 3,000 is equal to 2,000 E raised to the R, and the T happens to be 4, and I wrote T. The T happens to be 4 here. So solving for R, we're going to get R is approximately equal to 0.101. That's approximate growth rate. So then our equation P of T is equal to 2,000 E raised to the 0.101 of T. So that's our equation. After 10 years, all I'm going to do is put 10 in here. And so we have 2,000 E raised to the 0.101 times 10, which tells me that I'm going to have, after 10 years, I'm going to have approximately 5,491 penguins. Other thing that they're asking for is how long does it take to double? Now, if you remember from your pre-calculus 2, we have the natural log of 2 is equal to R times T, where T is the time it takes to double. We can totally use that. Or we could use the fact that 2,000 E raised to the 1.101 times T is equal to 4,000. Either way, I'm going to get an answer of about the big T. If I use the big T, I'm going to have the natural log of 2 divided by the rate, which is 0.101, which is the big T. Or I can use this equation. Either one is going to get me there. And I'm going to end up with about approximately equal to 6.86 years. And so that's the answer for that one. Newton's law of cooling and heating is another separable differential equation. So basically Newton's law of cooling, we use it in physics. If you decide you want to go into crime scene investigation, you can kind of estimate the time in which the body was killed based on the ambient temperature, the temperature in the area, and the temperature of the liver of the body. And you can kind of estimate when it was killed by Newton's law of cooling. So the temperature, T, is that of the body. The temperature A of the air is A. The rate in which it changes is directly proportional to the temperature difference from A air temperature minus body temperature. And we can express it in this form. T prime of T is equal to K, where K is our constant. It's a positive constant that depends on the physical properties of the body. A minus T of T. So, since we know that this is a separable differential equation, we basically do that and we end up with T of T is equal to A, which is the temperature of the air, minus alpha E raised to the KT, where alpha is equal to E plus or minus E raised to the C. And you're like, well, where did this C come from? And C is just that constant of integration. Let's go ahead and do an example here where we have a metal bar with initial temperature is 25 degrees Celsius, is dropped into a container of boiling water at 100 degrees Celsius. After 5 seconds, the temperature of the bar is 35 degrees Celsius. What will be the temperature after 1 minute? So what we have is capital T of T is equal to 100. That is the temperature, the ambient temperature of the air, or in this case, the air of the water, or the temperature of the water, plus, and then I'm going to have here 25, that's the initial temperature of the metal bar, minus 100, and then E raised to the negative KT, which gives us the 100 minus 75 E raised to the negative KT. Now we need to figure out what that constant K is, or in other words, the rate of cooling. We know that after 5 seconds we have a temperature, so we can put that in there. So after 5 seconds, the temperature is 35. So 35 is equal to 100 minus 75 E raised to the negative K, and then we have the 5 right there. Solving for K, I'm going to get K is approximately equal to 0.0286. And so after 1 minute, well, now we have our formula. So I'm going to go back to here and say P of T is equal to 100 minus 75 E raised to the negative 0.0286 T. So I'm going to put this in after 1 minute. And after 1 minute, we have approximately 86.53 degrees Celsius. Now, we want to know how long it's going to take for it to get to within 5 degrees Celsius. So what we're going to do is 0.5 degrees Celsius is we're going to set this equal to 99.5 degrees, which is equal to 100 minus 75 E raised to the negative 0.0286 times T. And we're going to solve for T, and we get approximately equal to 60.66 seconds. That's how long it's going to take to get the temperature up to about 99.5 degrees Celsius for that bar of metal in that boiling water. And that's it for this video.